Half a day, everyone. My name is Minas.
I'm Jordan Santos.
I'm Renee Marquez.
And I'm Kangsan Yoon.
Today we will be presenting Playing the Global Game, Modeling Effective Strategies to Combat COVID-19 on Guam. So it's pretty much common knowledge that COVID-19 stands for Coronavirus Disease of 2019. And it is an airborne disease, meaning that it can easily be transmitted through coughing, sneezing, and touching contaminated surfaces. Before we talk about our project, we'll give a short intro on Guam. We are an island territory of the USA with a population of about 150,000. We got our first case here in Guam on March 12, 2020, with vaccines rolling out in December of that same year. And as of last month, we have had 61,000 cases, 415 deaths, and more than 80% of our population fully vaccinated. Our main goal is to determine what strategy is more effective in stopping the spread of COVID-19 on Guam. To do so, we created 3 distinct scenarios: vaccination only, education only, and a combined scenario with both vaccination and education. We have 3 COVID-19 vaccine brands on island: Pfizer, Moderna, and Johnson & Johnson. Immunization starts 2 weeks after the second dose of either Pfizer or Moderna, or 2 weeks after the single dose for Johnson & Johnson, and we do recommend to regularly take boosters to stay immunized. Next, we define education as the practice of safety protocols such as wearing masks and social distancing.
The basic SIR model is used as a framework for how disease spreads. Using the SIR model, we are able to generate differential equations in order to model the spread of disease over time. In order to properly model our research, we need to make some assumptions. Firstly, no one in the population is immunocompromised. Secondly, people who get vaccinated will complete their chosen series and continue to get boosted. Next, it takes 90 days for someone previously infected to lose their immunity against the disease. Lastly, everyone follows the Department of Public Health Social Services, the CDC quarantine protocol. We expanded the SIR model to an SVEIJR model. This model takes the basic S, susceptible, I, infected, and R, recovered model, and adds the V, vaccinated, E, exposed, and J, isolated compartments. For our first scenario of vaccination only, we set our education level epsilon to 0 and analyze how our vaccination rate, nu, affects the spread of disease. In our second scenario, education only, we set the vaccination rate nu to 0 and analyze how the education level affects the spread of disease. The parameters needed for this model are calculated as rates per day using local data provided by DPHSS, with focus on the transmission rate beta, the vaccination rate nu, and the education level epsilon. Our differential equations are then found by taking the difference of rates moving in and out of each compartment. We can find the subpopulations of each compartment over a time t, and from there, the total population.
First, we define the disease-free equilibrium to be the state at which the disease is absent within a population. We denote the disease-free equilibrium to be E0, where compartments S and V are defined in our first scenario, and only the S compartment in our second scenario. We then derive our disease-free equilibrium to obtain our basic reproduction number R0. R0 is the average number of secondary infections caused by one infected person in a susceptible population. Using the next generation method, we were able to compute for R0. We keep in mind that when R0 is less than 1, the disease will die off, and when R0 is greater than 1, the disease will continue to spread. Since we're using the next generation method, we compute the Jacobian matrices to find the spectral radius of FV inverse, giving us the following equation for R0. Once we have the formula for our reproduction number, we're able to find the herd immunity for each strategy, which occurs when the susceptible population is immunized against the disease. This immunity is reached when R0 is equal to 1. With that in mind, we also generated a plot to display the threshold value for each scenario. After finding our disease-free equilibrium and R0, the next step is to find out what happens when a disease does settle into a population. So this is our endemic equilibrium, notated as script E star. The subpopulations E star, J star, and R star are all in terms of I star for simplicity's sake. This endemic equilibrium will come into play during the game theory portion of this project. But the next thing we do is perform a sensitivity analysis on R0 with respect to each of our parameters. This allows us to find out which parameters affect R0 the most, with greater values corresponding to greater influence. We find that nu and epsilon are the controllable parameters with the greatest respective values.
Now we can set up our vaccination and education games. The players in each game are individual people from Guam's population. The strategies are to vaccinate or educate or to not, and the payoffs are the costs of vaccination, education, or getting infected. With this setup done, we can move on to finding our Nash Equilibria, which are situations within a game in which no players benefits from changing strategies. Finding these will allow us to determine the optimal strategies in each game. To consider this, however, we will also need to find equations for the expected payoffs for each strategy. Starting with our vaccination game,
the payoffs deal with the cost of vaccination CV, cost of infection CI, as well as the likelihood of getting infected pi v to I and pi s to I. We get our transition rate by taking the parameter going into the next compartment over the total outgoing parameters. For example, individuals from the susceptible compartment travel to the exposed compartment through beta I star, and the total outgoing parameters are mu, nu, and beta I star, and we notate that probability as pi sub s to e. And we get our likelihood by multiplying all the transition rates from either s or v all the way to I. If the expected payoff for vaccinating is greater than the expected payoff for not vaccinating, the optimal strategy is to vaccinate, and if it's the opposite, then you would choose not to vaccinate. When in our disease-free equilibrium, nu at our Nash equilibrium will be 0, and in our endemic equilibrium, nu at Nash equilibrium will be the solution for the equation where the expected payoffs are equal. After that, we get our Nash equilibrium by solving for nu in terms of the relative cost of vaccination. Moving on to the second situation, similar to what we did in the previous, we take the cost of education CE and the cost of infection CI times the likelihood of getting infected. Same process with the transition rates. We take the rate going into the expected compartment over the rates coming out of the compartment. A significant difference is that we multiply beta by 1 minus epsilon and remove the vaccinated compartment to reflect an education-only environment. Then we find our Nash equilibrium by solving for epsilon in terms of our relative costs.
For finding our functions at the Nash equilibrium with respect to their relative costs, we can graph and visualize the points at which a player would adopt their strategy. Here in the green, it is optimal for a player to vaccinate, while the red area tells us when a player will not vaccinate. In observance of this graph, we can see that in order for the population to reach herd immunity at the value 0.7399, the relative cost of the vaccine must equal 0, basically free. However, even if there is no direct cost, there may be some indirect costs such as gas, time, etc. We can find the maximum relative cost by finding the point at which the population vaccination rate equals 0. This cost is the price at which no one will ever vaccinate, keeping the disease alive. When relative cost for education is 0, we expect all players to choose to educate themselves until herd immunity is reached and the disease dies. Not only could we check for the herd immunity value reaching 0.9126, we can determine the maximum cost at which no player would choose to educate themselves, which we found to be 0.995. Essentially, a massive need for education exists regardless of the population's education level. A player would educate themselves in almost every point while the disease is alive.
Now, we inspect the game in which both vaccination and education are available as strategies to each player. This is more applicable to what's happening in the real world as people have both options available to them. To begin our analysis, we must solve for nu at our Nash equilibrium in terms of epsilon, and epsilon at our Nash equilibrium in terms of nu. Our nu at Nash equilibrium in terms of epsilon is almost the same as the nu at Nash equilibrium of our vaccination game, except for that factor of 1 minus epsilon is added. Same goes for epsilon Nash equilibrium in terms of nu. These equations are actually based more closely on the general model from the beginning of the presentation. The next thing we do is find the values of nu and epsilon for which epsilon Nash and nu Nash respectively equal 0. We call these nu naught and epsilon naught. When we compare nu naught to nu at Nash equilibrium and epsilon naught to epsilon Nash equilibrium, we can find out which strategies end up being dominant. These are the inequalities corresponding to the dominance of either vaccination or education. When nu naught is greater than nu Nash equilibrium and epsilon naught is less than epsilon Nash equilibrium, education is dominant. When nu naught is less than nu Nash equilibrium and epsilon naught is greater than epsilon Nash equilibrium, vaccination is dominant. The other cases have to be inspected more closely to find out for what nu and epsilon either strategy is dominant. We can then create equations of the relative cost of vaccination in terms of the relative cost of education, first based on nu naught is equal to nu at the Nash equilibrium. Then based on epsilon naught equals epsilon Nash equilibrium. When we graph both of these, we will find that different regions of the graph correspond to different mixed strategy inequality cases, the same as these. Here's the plot containing graphs of the relative cost of vaccination against the relative cost of education derived from epsilon Nash equilibrium, the line in red, and nu at Nash equilibrium, the line in black. The purple region represents the set of relative costs for which the education strategy is always dominant, and the beige region represents the set of relative costs for which both strategies are dominant depending on the values of nu and epsilon. There is no region within the bounds of the maximum relative cost for which vaccination is the dominant strategy. On this slide are examples of the plots obtained when selecting points on the previous slide's graph and plotting the two equations, nu naught equals nu Nash equilibrium, and epsilon naught is equal to epsilon Nash equilibrium, represented in red and black respectively. When the red line is above the black line, education is the dominant strategy. And when the black line is above the red line, vaccination is dominant. When they intersect, we obtain the mixed strategy Nash equilibrium as seen on the second graph. So now knowing all this, we revisit our original question. What is the best way to combat COVID-19 on Guam? The answer will either be purely education or using a mixed strategy. So let's go over some of the results before we answer. Over the course of our research, we determined that costs of vaccination, education, and infection would include the perceived risk of each, the potential loss of time, and either physical, mental, or emotional effects. The cost of vaccination for which the relative cost of vaccination is maximized is approximately 2.125 times 10 to the negative 4 times the cost of infection, while the cost of education for which the relative cost of education is maximized is approximately 9.953 times 10 to the negative 1 times the cost of infection. The relative cost of education is approximately 4,683 times the relative cost of vaccination. In our pure strategy case for education, the maximum cost for which people were willing to educate was much larger than the respective cost for which people were willing to vaccinate.
Despite the cost of education being roughly equal to the cost of infection at the threshold, we predicted that the population would usually opt to educate themselves instead of vaccinating because of the limits placed by the maximum relative costs of each pure strategy in our mixed strategy. Function of epsilon naught is less than epsilon Nash equilibrium occurs indefinitely. In our mixed strategy, the vaccination strategy is never purely dominant. The slightest increase in the cost of vaccination drastically reduces the population's vaccination level, while the population's education level only changes after a significant increase to the cost of education. Because the maximum relative cost of vaccination is so small in comparison to the maximum relative cost of education, we can only determine the mixed strategy the closer we are to the maximum cost of education. So, knowing this, we can conclude that the best way to combat COVID-19 on Guam is a mixed strategy involving both education and vaccination.
Our next goal with our model include the following works. 1, evaluate each component for the mixed strategy of vaccination and education. 2, propose and apply our game theoretical approach to outreach programs through DPHSS. And 3, collaborate with DPHSS in measuring the education level on Guam. And that concludes our presentation. Special thanks to our sponsors for the Young Scholars Research Experiences in Mathematics through the MAA TensorSumo program and the MAA National Research Experience for Undergraduates program. Special acknowledgements to Dr. Hyunjin Oh, Mr. Vince Campo, and research assistants Cabrini Ugin and Jovica Asi. Finally, special thanks to the Department of Public Health and Social Services for the data provision. And these are our references.